So the question is that if all musical instruments can produce the same frequency sound, then why is it that we are able to distinguish very clearly between the sound that is produced by a piano, an electric piano, and a sound that is produced by a tuning fork? Okay, so nobody will have any problem distinguishing between these two sounds. So I'm waiting for Tanvi and at least Tanvi to get her instrument tuned and ready.
Time my mom.
Yeah, that's not a problem. Just let me know whenever you're ready, so that we can also hear the same note being played on that. Are you going to be playing it, or is your mom going to be playing it?
My mom. I don't know how to play the violin at all.
So she's there then. Hello.
She'll come in a few minutes. She's not yet here. Like she's doing something. She'll come in like probably 5 minutes.
So today's class, even if we don't do anything, at least we have the piano and the tuning fork. We'll work with that maybe by next class. Now that you understood that I'm serious about this, maybe you will all get your instruments ready. How do we figure this out? Okay. So the thing is that if pure frequencies are the ones that are being played by any musical instrument, then obviously we are not going to be able to make out the difference between the different sounds. The fact is, there must be other frequencies that are also mixed in with these frequencies, and that is the reason why we are not able to we are able to distinguish between the same notes produced by different instruments, including the human voice. Now, how do we know this to be true? Well, one of the first things that we have to know is that musical notes also get superimposed over one another. So if you remember in the last year, we did a little bit of work about the superpositioning principle. That is, if there are two mechanical waves or more than two mechanical waves produced in the same medium, then these waves can either add to each other's amplitudes or they can subtract from each other's amplitudes. Okay, that is if the waves are having the same frequencies. If the waves have different frequencies but at the same time have different amplitudes, then what happens? Okay, so with waves of same frequency, we should be able to easily show it by just drawing some diagrams of the wave function, and I will just do that in a moment now. Remove the piano first. I'll just keep it aside. Let it be. So, if you can just move to speaker view and pin my screen so that you will be able to see it clearly. So, what happens is that if you have two waves,
Sir, can you make the second one on the right instead of below it, because we can't see the thing below.
I'll move it up. Fine. Now are you able to see it?
Yeah.
So if these two waves come in the same time, okay, then what's going to happen is that these two waves are going to superimpose each other. So it's going to produce a wave which, depending upon their amplitudes, will get added. So if these two amplitudes are exactly the same, then the amplitude of this is going to be twice the amplitude of this one. The other consequence of this is that, of course, if one wave is out of phase with this wave, right? So if it is like this, right, then it is going to produce a resultant wave with zero amplitude, because the peaks are going to cancel with the peaks because they are at the same time. You can imagine them as two waves being produced at the same time. One is one frequency less than the other. So you start one off, and then when the first one is stuck, then the second one is also stuck. So they are kind of like out of phase with each other, right? Then it is easy to see that the cancellations are going to take place. So the potential the high potential of this particle at this point will be cancelled out by the low potential of this particle at this point. So that will result over here, sorry, that is this part, right? So over here it will result in a wave that has zero amplitude. Okay, so this is easy enough to understand. Now, what if you have waves that are of differing frequencies? Okay, there is one wave over here. What if you have, instead of one wave, two waves over here? Okay, we can apply the same principles over here. That is by looking at this point. I'm starting by analyzing that point, but let us see if that works out well. So this wave, that is, let me label them also. So for wave A, and it will be good if we are also able to give some time frame for this. Let us say the time over here is 1 second. So the time over here is also 1 second. So this will be 0.5 second. Okay, so we are talking about 0.25 seconds. What happens at 0.25 seconds? The wave A is at its maximum amplitude that is possible. Okay, the wave B at the same time frame, that is 0.25 seconds, is at zero amplitude. So what can you say about the resultant wave at 0.25 seconds?
Will be the max amplitude of A.
Yeah, so the resulting wave will therefore be at the maximum amplitude. Is there any difficulty in understanding this? Is there any difficulty in understanding this?
No, sir.
No, okay, thank you. At least two people said they didn't have a problem understanding. Okay. So tell me one more point where this will get illustrated well.
Like the tip of the tip of wave B,
No, tell me the time.
0.75 seconds.
0.125.
0.125. Okay, that is here you mean.
Yeah.
Okay, so at 0.125, the wave is at this point. The particle has that particular amount of energy and it is at its peak over here. So what will happen to that? The max incidentally is like over here. Let us say the amplitude of this wave is half the amplitude of this wave. So now where should I draw the point over here?
The maximum function.
Think.
Can you do that?
Can I repeat? Do you want me to repeat?
Yeah.
Okay, so when comparing it at 0.25, it is clear that this is at max amplitude, okay, and this one over here is at zero amplitude. So therefore, whatever the max value, it came out only that, okay, because basically it's an identity function. You have maximum amplitude over here, zero amplitude over here. If you add those two, it will come to max over here. Now, Saumitri suggested that you compare it at half of that, that is 0.125, is it? Yeah, 0.125 seconds. At that time, this wave is at its max, which is its half the amplitude of that one. Okay, Kirti is here, just a second, I'll admit her. And this wave is at also half the amplitude.
Will still be max, right?
Exactly. So it is still going to be max over here. Sorry. Okay. Will there be another point at which we can compare it?
Half of that. No. Yeah, half of that.
Half of
0.6, 0.65. Okay. Yeah, 0.625 only.
0.625. That is here or here. No, that is 0.75. Right?
I think what Samantri meant was 0.00625.
Oh, half of. You mean somewhere here?
Yeah, I don't know actually.
Yeah. So the
No, I
point.
meant the one between those two. Like
Okay.
every wavefront.
Yeah. So the point being that we can see that already when we have double the frequency with half the amplitude, adding up the two waves can become pretty difficult. Okay. What we will have to do is we will have to see how each point corresponds to the other point and in what way will they add up or in what way will they affect each other. Okay, and therefore the wave front over here is hard to imagine what it's going to look like over here. I mean, we can spend some time analyzing this thing and actually show what the pattern is going to look like, but that's not going to be, strictly speaking, easy. Okay, and therefore we are saying that it is possible that there are two sound waves with different frequencies, in this case twice the frequency of the other but with a lesser volume, which can combine together and give us a sound which is a result of the addition, a superimpositions of these two waves. Okay, now the question is, what is that going to sound like? All right, are we going to be able to hear two distinct waves, or we will hear only one wave but which has characteristics of both these waves? So that is the fundamental question that we are asking in terms of what is going to happen. It went off. Let me just check what. Okay, now analyzing this kind of sorry. Yeah. So analyzing this kind of a thing, what can I say, in an analog manner, that is doing the mathematics of it, is obviously going to be pretty difficult. Not in this case. In this case, see, the solution, of course, is to make a cyclic function for this. You can use a sine function for this and construct a sine function and another sine function for this, and then you can actually add the two sine equations and you can give a trigonometric proof of what is going to happen as a result of those two things. Okay, but when you have complex waveforms of the kind that are produced when musical instruments are played, even pure notes like, right? What you really want to do is, what we are saying that we need to do is, we need to do the reverse of this. We need to actually deconstruct the wave pattern that is created by the sound into its constituent frequencies. Okay, and that definitely is not an easy task to do. It actually cannot be done analytically. It will have to be done computationally. Okay, and the computation was invented by Mr. Fourier, I suppose. I don't know his name. I don't know his full name, but the mathematics that came out of this was called Fourier analysis. Okay, so is it kind of like clear what we are talking about now? I will also give some examples of how that Fourier analysis can be done. But as of now, is it clear what we are talking about? Patanjali,
Yeah.
yeah, if anybody has a sitar and a guitar, just get it. What I want to try, actually, yeah, at least Patanjali, get your sitar. We will try
Sir,
it. Yeah, Krishna?
sir, sir, it's Ami.
Anya, sorry. Go ahead.
Ami,
Ami, sorry. Yeah, you told me that you will get some instrument.
I have a recorder also, and it's like a flute.
Yeah, I know it's a recorder. I was looking for my recorder. I couldn't find it. Recorder is really nice.
Should I get it?
Yeah, get it.
Okay.
It's not going to take too much time. Okay. So what I'm asking right now is, did you get the fundamentals of what we are talking about? If anybody has any questions, you can ask now about this. So to carry on with that, I hope you understand the task, which is that what we have to do to see whether what assumption we have about the differences in sounds produced by musical instruments is because of a complex mixing of different frequencies that take place, is the one that produces the particular quality of sound produced by the instrument. These two do a deconstruction of the wave pattern produced by that musical instrument. That deconstruction is not an easy task. We had to invent a kind of a branch of mathematics to be able to deal with that, which comes under Fourier transformations or in this particular case, Fourier analysis. And thankfully for us, Fourier analysis can easily be done using a tool like Audacity, and which is what we are kind of trying to do it now. I haven't done this before. Many years back, Kishore sir helped me to do Fourier transformations using a kind of a computer very much like the Raspberry Pi. It is called as Phoenix, and you could kind of connect it to a speaker or a microphone. Actually, in that case, it was the same thing, and pick up sounds produced by different musical instruments and use a program to actually do the Fourier analysis directly. Now, there is a very nice video which I will send a link to the Google Classroom, where you can look at to understand Fourier analysis, which is created by one of these channels that does mathematical simulations. Once we have done the task ourselves, then perhaps looking at the video might help you. That is why I didn't send the video earlier. Now I'll shift to Audacity and I will try to play some sounds so you can see what recorded sound looks like when you do a waveform of it. Okay, so I'm moving to screen share with Audacity. So I hope you're able to see the screen now. We have used Audacity once before, but we haven't used this particular aspect of it. So what I'm going to do is I'm going to play the middle C and I'm going to record the sound. And let's just look at the sound to begin with. Okay, so I've captured the sound now, and this part of it is probably just the background sound because I didn't strike the key at that time. And here when I struck the key, the amplitude was very high. And then because of the damping effect that takes place, the amplitude reduces and it kind of sustains over here. Okay, so first of all, let's just magnify this and look at what it really looks like. Okay, it kind of like, to begin with, it doesn't look anything like waveforms that we have seen till now. Okay, and now I have kind of amplified it to quite a large extent, and then you start to see the repeating wave patterns. Are you able to see this?
Yeah.
Right? So again, my suggestion is if you're not able to see it properly, first of all, watch on a laptop or a desktop, and second thing is switch it to speaker mode and pin my screen so that you can see the whole thing. Okay, and here now you can see that there are repeating wave patterns. You can see this bottom repeats again and again over here. Okay, and the top of it also kind of repeats over here. So there are two kinds of waves, one with this double hump and this smaller hump over here, another one with the bigger hump and the smaller one. So the two ones and the small one, and one big one with the small one, then two, and then it kind of repeats. So you see the repeating patterns. Okay, now what we have to do is we have to break down this wave by using the reverse of the Fourier addition. So do a reverse Fourier transformation on this and get out what all the constituent frequencies are. Is this clear now so far? Any questions?
So,
No. Okay. So for to be able to do that, there is an analyze button over here. So in the menu, so in the analyze, there is something called plot spectrum. Okay, so that is what we are going to use. But it will not plot the spectrum unless I tell it from where to where I want it to plot the spectrum. So I'm going to choose a specific area where I see that the amplitude is not varying by too much. Okay, and I'm going to do the plot spectrum on that area. And when I do that, I get a frequency analysis that looks like this. Okay, so I'm going to give you a few seconds to look at this and tell me what you see. And of course, there isn't any specific right answer or wrong answer about this. Just look at this and tell me what you see.
So where's the frequency analysis?
Beg your pardon?
Where is the frequency analysis? You said something like is there. We can't see it. And you must be sharing this tab.
No. Oh yeah. Okay. Is it that I'm just sharing the tab?
Yeah, you'll have to screen
Maybe.
share
Maybe.
your whole screen.
Yeah.
You still don't see it?
Now we do. It's purple.
Yeah, we can see it.
Okay. Good.
Yeah.
I'm just trying something out in this. Maybe not. I think this is the best view that is possible. And if you want me to do something on the screen for you to see, then I can do that also.
There are lines.
Boom, man. Very funny. Like it's a graph. It's a graph, right? Just tell it. Basic thing that you can tell is what's on the x-axis, what's on the y-axis.
Yes. Frequency and the loudness of the sound.
Your volume is pretty high, so either speak a little bit away from the mic or reduce the volume on your mic. So there is, thanks, frequency on the x-axis and the loudness of the sound, okay, in decibels on the y-axis. Okay, so how is this helping us to understand anything?
Higher the frequency, lower the sound.
Yes, that is one thing that happens. What is this? So is it that for different frequencies the volumes are different because we just analyzed one instrument and I played the middle C, which is supposedly what frequency?
256.
256.
Middle C, I don't know. Just check on Google what is middle C. Is it 256? You're sure?
It's something like 256. Not exactly.
Around 256.
261.625565.
Yeah. So can you look on the graph and kind of locate where 256 is?
Oh, then it should be 261, like Ara said.
Why 251 in particular?
It's 262.
262.
261.
262, 261, okay. See, we played 256. Why are so many other frequencies also showing up over here?
Background noise?
No, not so much. You sure? Why background noise?
The damped vibration, right?
Yeah, damped vibrations.
Yeah.
The amplitude is decreasing, so does the frequency.
What was that, Abhi? Can you repeat that?
So, since it's damped vibrations, the amplitude and frequency keep decreasing, right?
No. Why would the frequency change?
Oh, sorry, the amplitude.
The amplitude changes, yes. Nothing conclusive, that means. This particular Fourier analysis did not tell you anything. Or is it that maybe we don't know how to read this particular chart?
Yeah.
Okay. I think what I'll do is I'll take a screenshot of this and post it for anybody who wants to look at it and try to understand this. Okay. I'll post it on the classroom. Maybe we can try something else. So I'm going to close this and I'm going to delete this. What if I did a pure frequency? Okay, and I know that a tuning fork will produce a pure frequency. So I'm going to try it. Okay. Okay, so you're able to see the Audacity screen, right?
No, sir, you haven't shared that one.
Oh gosh, wait. Now what are you seeing?
Now
Yeah,
we're
and
seeing the analysis page.
Now can you see this? Now can you see the screen? No.
no.
Now?
Which screen? Which screen?
Yeah, now we can.
Yeah, I have the tuning fork recording.
Oh yeah.
You can see
Yeah.
it? So I'm going to again can you see the tuning forks
Yeah.
waveform? Which one looks neater, the tuning forks waveform or the waveform produced by the piano?
Tuning fork.
The tuning forks, right? Because in the piano's note, what we saw was that there were irregular waveforms, right? Whereas in the tuning fork, it looks cleaner, much closer to how we are representing sounds in terms of diagrams. So I'll do the analysis on that. I have to choose. Why don't I choose it from here? Okay. Uh, Not enough data selected. So I have to use a much larger data. Hopefully that will be enough. Yes. Okay. So are you able to see the analysis plot?
No.
Why can't I just share my screen so that whatever I'm seeing, you're
You
also
can. So
You can,
you can
but you'll have to
stop screen
stop and
share and
then
then
restart.
and then start again.
Oh, okay, I got it. So next time I do it, I remember that. Yeah, can you see it now?
Yeah.
The plot analysis. And
Yes.
again, now it's the same thing. You have the y-axis showing the loudness and x-axis showing the frequencies. But can you see these spikes?
Yeah.
Okay. So now what I'm going to do is I take a screenshot of this also, and I'm going to post it on the Google Classroom. Okay. And I'm going to wait until next class for people to come up with some explanation of what is going on over here. Okay, and you can use the document that I have posted on using Audacity for Fourier transformations and these two screenshots to be able to come up with an explanation of what is happening over here. Okay, so until that happens, we will wait.